Welcome to the Australian Water School, the home of demand-driven industry-designed training for the global water sector.
Welcome to another great Australian Water School webinar. It's going to be a good time, I'm sure. There's so many joined up already and many coming on board as we speak. Thank you for joining us again. Next Generation 2D Hydraulic Modelling, presented by Phil with Bill and Shuang. That's the A team from TUFLOW. Sorry about the other colleagues, people, but that's great to have you. I'm Trevor Pillar and I'll be chairing today. Thank you for joining us, everyone. So many have come in. Look at this, across the world. A lot in Australia, a lot in North America, Europe, India. Yep, that's a great spread. Look forward to this discussion today. It's going to be fantastic. Well, let's get right into this. Phil, 15 years experience working on numerical hydraulic modelling tasks. Good to see you coming on screen. Phil is currently software development lead for TUFLOW Classic HPC hydraulic modelling software. Bill Syme has over 30 years experience in flood hydraulics field. TUFLOW software was developed by Bill starting in 1989. Bill is a software business lead managing TUFLOW products and associated service. Shuang Gao is an environmental engineer, software developer. Main interests lie in the development of cutting-edge modelling methods applied to real-world engineering problems. What a team. So glad to see you all here again today, guys. Just before we get cracking with this, Phil's going to do the presentation. Bill and Shuang are going to be answering any questions you have. And please, by all means, get stuck into it now. Hit that Q&A icon at the bottom of your screen there. Just before we do that, there's that poll that you so kindly filled in, everyone. Thanks so much for this. What sector are you from? Government and commercial win there. No surprises, I suppose. Any comments, gentlemen, as we go through? What hydraulics modelling softwares? Well, TUFLOW gets a big kick there, as does Hecros, of course. Yeah, lots of others there. How many years?
Yeah, relatively top heavy. It's probably pretty consistent with what we've seen with some of these other ones. Question number 4 is interesting on what percentage of hydraulic models are using 1D open channels. It's actually with the blip in the 0 to 25. There's the rest of them are all hovering about 15 to 20%. So it is a pretty consistent spread across those range.
Yeah, sure. Good, interesting feedback. Yeah.
And look at the last one. Well, there's your answer for today's webinar. This is why we need to do this webinar, gentlemen.
Yeah,
all right.
It sure is. And there you go, Phil.
It's
all
open book. Yeah. Thanks so much. Thanks so much for those poll questions answering everybody. Handing right over to you, Phil. Shuang and Bill will be on the Q&A channels. Hit them hard and hit them often. No, nothing's too hard for them, right, Bill? Did you say that?
Yeah.
Nothing too hard.
Nothing too hard.
Over to you, Phil.
I presume everyone can see my screen.
It's
come through.
Great. Yep,
excellent. Let's kick on then. Yeah, well, welcome aboard, everyone. Thanks for coming along. Quickly, the agenda of today, we'll have a little bit about 1D and 2D linked modelling and why we use it, and then we'll jump into some benchmark case studies. One being a hypothetical trapezoidal channel, and then we'll move into a real-world open urban catchment. So I guess one of the main questions we have when we start off modelling something as hydraulic modelers is whether we're going to model it as 1D or 2D. 3D is not particularly common in terms of the flood modelling that we do. So, usually for most flood modelling applications, we'll be looking at modelling it as either 1D and 2D. And there's distinctions between those and advantages and disadvantages of each of those. Particularly when it comes to the open channel modelling, the 1D is often harder to set up. There's more work in setting up 1D cross sections and particularly if you're linking that to a 2D model in setting that 1D, 2D linking up. The benefit of the 1D in particular is really in terms of speed, the ability to simulate that faster. That does come at a price though. There's a range of other considerations that you need to have when you're modeling it in 1D, such as when you're modeling in 1D, you need to predefine where the water can go. You need to set your flow paths, set your model channels and sections to allow flow in that. Whereas with 2D, it's taking into account a DEM and letting water go where water wants to go. I won't go through that whole table there, but there's a bit of a considerations for 1D and 2D. We'll talk quite a lot about some of the turbulent losses and also junctions as well in this presentation. In terms of mapping coming out, there often is a little bit of work to get 1D results to look nice across a spatial plan map, whereas with 2D modeling, it really comes out of the solver is a spatial output. So they're certainly easier, and I think we see that with the preference that on the poll was over 75. I think it's about 75% of people would prefer to model it in 2D rather than in 1D, and I'm guessing that that's part of the reason. 2D equations are also probably much closer to reality when it comes to some of those influences like turbulences, junction losses, things like that. In terms of the topography of those open channels, traditionally when we're modeling this as a 1D, we need to get sections surveyed, and they're normally surveyed across the channel at regular or discrete locations. They might be every 100 meters or something like that. And so the surveyors have to go out in the field and grab those, survey those sections, which does make it a bit slower to set up. What we're seeing now is that the technology is getting better and cheaper, and things like laser side scanning actually becoming more prevalent than actual surveyed cross sections. So instead of in individual locations where you have sections, you actually get, like we have in this image over here on the right hand side. I'll just turn on my pointer. We've got actually a full bathymetric survey of that channel, which does actually make it a little bit easier to set up than 1D. In terms of setting up 1D, 2D modelling, as Trevor, I think you mentioned in the introduction, Phil's started TUFLOW in the late 80s, and actually it was a master's project in terms of linking a 1D model with a 2D model, was actually the crux of Bill's thesis. And in its initial form, it was something like this. So where we had 2D in a small area where we were in an area of interest, largely because it was very slow and computationally intensive to run 2D models. So the 1D was used to get the water into and out of that 2D without having two separate models where you have boundaries and exchanges of information. And back in the glory days of that, 1990, there's an example from Australia, from the Gold Coast Seaway. So we can see these dots here are actually 1D components feeding water down into a 2D, where we've got a 2D now narrower area of interest around that Gold Coast Seaway. Then moving on, we've sort of moving towards actually modelling conduits and cross drainage structures as 1D elements embedded within a 2D, and that's not necessarily done for a speed reason, more because that's difficult to represent those in 2D. So that's largely the reason there that that's modelled in 1D rather than in 2D, and that's still very commonly done. And getting to I get the crux of what today is about is replacing 1D open channels with 2D. That's been in TUFLOW since early 2000s, and it was used to allow 1D in that channel to have a good representation of those narrowish open channels compared to the floodplain, and then dynamically link those to the 2D. So we have a single model, which is we're representing those urban channels as 1D and then linked to 2D. And that's probably still something that we see reasonably commonly done. And largely the reason for that was the 2D, if we tried to have 2D representation in there, we'd end up with very long runtime, particularly before the advent of the subgrid sampling. We'd have had to have very fine resolution cells in that channel to be able to represent that, and that will have certain implications on runtime, and also back then 32-bit software memory issues as well. So it wouldn't really have been possible to model at it purely as 2D or a 2D in the open channel back then. So that's an example, and this is actually a model that we built back in 2006 and have sort of revisited for this webinar. So that's an example of the original output from that study. So we've got red water level contours and depth and velocity outputs. So in the main channel here, it's 1D and dynamically linked with 2D. So what's changed? As I mentioned earlier, the in-bank bathymetry is getting better and cheaper rather than sending surveyors out to get discrete cross-sections. And there's also been a few advents in the hydraulic model. So the subgrid sampling of both elevations and materials, so land use or Manning's N across at a subgrid resolution. Also, there's been some changes in terms of how we handle structure losses and things like that, mean that more people who are using TUFLOW are probably looking at getting those into 2D. The other big caveat that's not in here is hardware improvements. Speed's becoming less of an issue, particularly with the advent of GPU compute. And when we can get our hands on the latest and greatest generations of GPUs, wrestle them off the cryptocurrency miners, they're phenomenally efficient and very, very large amounts of hardware compute capability in those GPUs. So going to a very simple text case, if we have a rectangular channel, 1,000 meters long, 100 meters wide, with a simple fixed rate flow, fixed slope and Manning's N across there, it's very easy to compute what the theoretical value, what the answer should be for that. And if you run a 2D model of that, you should get exactly that answer. Before the SGS, the subgrid sampling in TUFLOW, if you start to rotate that model around, particularly with a reasonably coarse resolution across that cell, you would start to see there's a slight shift away from that that answer as you rotate, as your channel is not rotated to your to match your grid resolution. With the advent of the subgrid sampling going in there, we start to see that even irregardless of the mesh resolution, we start to get a really good consistent answer across there. That previous slide, so we can be confident that we'll get the right answer. You know, we don't have to worry about our cell alignment, and we should get the right answer. You know, with our model in the open channel. But that previous model has a constant elevation and Mannings across that channel. So if we start to look at something more realistic, in this case, I've got a compound trapezoidal channel. So we've got a concrete 10-meter wide section in the middle there, 4 meters deep, about a slope of 1.5 horizontally to 1 vertically, and then a 2D floodplain, which is a higher roughness. So in this case, 0.045. So something more indicative of you know, a grass or, you know, thick grass or something like that, light vegetation. And so 2 floodplains, one on each side, obviously, and the similar width as a channel. So we've set that up as a test case, and we've applied a downstream water level boundary and an upstream flow boundary to that model. There's no easy Mannings calculation to get an answer exactly for that directly. So we look at a 1D parallel channel analysis. So if we split that section up into a number of little panels, and if we do a conveyance calculation across there and work out the conveyance of each of those panels, we can work out what the total flow should be for a given slope, and that takes into account the variation in elevation and also Manning's value across that channel. So if we do that for that particular channel that I described, that's the flow versus depth curve that we get. So at about 500 cubic meters a second, we're expecting to see a water level or a depth in that channel, main channel, just above 4. What we did was we ran that as a model with a range of cell sizes all the way from 60 meters. So the total channel width there is 60 meters. So all the way from 60 meters down to 1 or 2 meters across there. I think in this presentation, I've only got down to 2 meters. We did actually look at going further down, but the trend still holds. As I said, we run that for a 500 cubic meter flow event, and we can use that parallel channel analysis to work out that the depth is expected to be around 4.27, and that's what's being used as that downstream boundary. So as I said, it's about a 4 meter deep channel, so we're expecting to have shallow depths on those overbank areas where we've got the high roughnesses. Okay, so if I jump to some results, what I've got over here on the x-axis is cell size. So larger cell size over here at 30 meters, down to a higher resolution cells at the bottom. So in this case, this red line is with the subgrid sampling turned off, and also with turbulence turned off. So there's no 2D turbulence taken into account. We've actually suppressed the turbulence term. So no shear between the main channel and the overbank, which is consistent with a 1D parallel channel analysis. So we can see that at coarse resolutions, we're not getting a great representation of that. We do actually need to have a few cells across that to actually account for that. That's because with subgrid sampling turned off, we're only sampling those elevations essentially at the cell center and cell faces, as well as the Manning values. So there's a lot of, until you start to get a smaller cell size, you aren't accurately capturing that topography in that channel. And if you can't capture the topography, one of the key things to get right is the flow area. If you can't get the flow area right, you're not going to get the head drop correct. So the blue line there is with the subgrid sampling turned on, and the green lines with the subgrid sampling turned on with the material sampling. So the sampling of Manning's ends at each of those subgrid sampled locations as well. So in this case, we were using a subgrid sampling resolution of about half a meter typically. So getting a much finer resolution than the cell size. For all cases, we do start to converge down to the parallel channel answer. But it happens much quicker with subgrid sampling turned on and also with the material sampling. turned on as well. Dashing out those lines with no turbulence. So I've kept them in there, but just made them dashed. Now I'm looking at the same cases with turbulence turned on. So in the red case, subgrid sampling turned off, but with turbulence turned on, just as the default terms. And blue is the same as the dash blue. It's with subgrid sampling turned on, but this case with turbulence turned on. And finally, with the green, with both subgrid sampling and material sampling turned on, as well as the turbulence. So all three of those, once again, are converging to a similar answer, which is higher than with the turbulence on. It's higher than the parallel channel analysis, which is what it's to be expected, because that parallel channel analysis and 1D solvers don't account for the turbulence caused by velocity variation across that channel. What we'd expect to see is out here on the right hand side is because we've got lower roughness and higher depths in the channels, we've got a higher velocity in the main channel, and then we've got a lower velocity, much lower velocity on the overbank areas, and that causes a turbulence and shearing across that channel. So we can see that in an overhead aerial photo here. You can see the turbulence forming, and over here is a lab scale. Where we can see the main channel over here on the right, flow direction here, and we can see this turbulence happening out here on the bank. And so these are actually photos, I think, that came from lab mates of my colleague Chuang Gao, who's in the Q&A line from his PhD, which he did in turbulent stuff. So tricky questions, feel free to ask away. Moving on, I'm not sure, you may have seen in an earlier slide, I actually referred to the case with turbulence turned on as isotropic turbulence. To differentiate that to anisotropic turbulence, so in anisotropic turbulence, we're separating the viscosity coefficients into a longitudinal and a transverse components. So we're putting a higher coefficient in the direction of flow. So the longitudinal coefficients are typically higher than the transverse coefficients. So in this case here, we've got a hypothetical tracer, with a uniform flow down a channel, and what you see is there's more smearing in the direction of flow compared to across the direction of flow. And that's partially due to a vertical profile. If you have a look at this, we're talking about 2D depth average solvers here. In reality, there is 3D flow effects going on, and you don't get a flat profile in the vertical. There is actually a vertical difference, and that drives part of this extra turbulence occurring in the longitudinal direction as opposed to the transverse. So if we compare to some measured velocities across a channel for a flume experiment, so in this case over here, we've got the crosses here. It's actually, and I realize this is quite a busy graph. The crosses here represent measured velocity across that profile. So main channel in here, and we've got a higher velocity in that main channel. Sorry, excuse the background noise. And what we're seeing there is the red cases with isotropic turbulence, where we've got a higher velocity in the overbank area compared to the measure. So there's more smearing. So there's probably too much momentum transfer across the channel. The black line is the case with no transverse term turned on. And the yellow and the blue lines are somewhere in the middle. So the blue case has more of the longitudinal turned on compared to the transverse. So if we add that to the previous slide, so in this case, the yellow line is with that anisotropic turbulence turned on. In this case, we've got a transverse value of 0.5 and a longitude value of 7. So more than 10 times in the longitudinal direction. So anisotropic turbulence is something that we've put into the TUFLOW solver recently. So that'll be available in the 2021 version. And we can see that reduces the head drop in that main channel. It also does flatten out that profile, so we see less impact of cell size. Okay, so conclusions from that, I guess, based on the initial rectangular style, we don't need to have our channel aligned with a cell with SGS enabled. And for a 1D and a 2D scheme without turbulence, as we expect, we get a good match between those results. When we start to introduce those turbulence and we have a cell size which allows for a velocity variation across the channel, that 2D provides higher water levels as would be expected. As I said, you do need to get a number of cells across that channel to get that velocity gradient correct. And it's starting to look like the anisotropic turbulence generates an improved velocity profile, and that's consistent with literature where we have longitudinal rates that are higher than transverse rates. So moving on from sort of theoretical stuff into a real world case, here we've got an urban catchment and Thoresby Cottage Creek. This is actually originally work that we did in 2017. Which was a detailed flood study. So data compilation, develop and calibrate models, both hydrologic and hydraulic models, and the full range of design event modelling, which follows the New South Wales flood management guidelines, which we adopt here in New South Wales. Notably, it had a really good calibration data set, which I'll speak a little bit more on, and also really high quality input data sets. Some of you may recognise this from a previous webinar we did in February on direct rainfall, comparing direct rainfall with hydrology. And there's a link to that webinar if you're interested. So that's the catchment there. So Newcastle in New South Wales, just north of Sydney, population of about 450,000, with a really highly urbanised catchment, with very heavily engineered system, so concrete open channels, culverts. You can see very straight channels. That's the main channel for the Thoresby Creek, is sort of straight as an arrow for a couple of kilometres. And what we've got is calibration data to 1998 and 1990 flood events. Notably, really high quality DEM. So the overbank areas is photogrammetry. There's actually a longitudinal survey of all of the main channels. So survey of the thalweg and the toe and the top of the batter, which actually allows for cutting cross sections basically anywhere along that open channel because of its longitudinal survey. So a very nice data set to work with, and also good quality data for all of those structures. Okay, and that's an example of what that DEM looks like in the main channel area. Some quite detailed land use mapping as well, and so that's what we're going to start with as our base case. So as I mentioned, this was actually originally work that was done back in 2006, 2007. What I've done is actually take the version that we created for the previous webinar in February and use that as the basis. So the original work was done with TUFLOW Classic back in 2007. It was using a fixed 10-metre cell size, with 1D in the in-bank. As part of the previous webinar, we actually kept the same 10-metre cell size, switched to the latest version of TUFLOW, used a GPU solver HPC with subgrid sampling turned on, and that's essentially become our base case here. So that's what we're going to compare with. So 1D in channel, 2D in O-bank. And we've stuck with the direct rainfall modelling, so with the SGS on and direct rainfall. And that's I think that's a duplicate of an earlier image on what the 1D, 2D channel representation looks like. So linking on the top of the channel. In terms of the data, yeah, good quality data. There's actually 11 pluviograph stations within or close to the catchment. And in terms of the magnitude of the event, somewhere between 370 and 450 millimetres over a couple of day period. And notably, we actually had some decent in-bank calibration. So I'm not sure about other parts of the world, but here in Australia, it's quite rare to have good stream gauging in urban catchment, or any stream gauging in urban catchments. So in this case, we did have three gauges in the main channel, and a range of flood marks as well, which we actually calibrated into have split into different grades. So the grade 1 being the highest quality, the most reliable. So it's high watermark in a building would be an example of a grade 1 mark. And as we move down to grades 2 and grade 3, there might be a reliable observation, but maybe it's not at the peak, or a rough observation is what we consider grade 4. So for the purposes of this webinar, we've really just focused on the in-bank data and also on the highest quality grade 1 flood marks as well. So if we have a look at the 1D, 2D calibration, that's shown there on time series in those gauge. So notably that middle gauge, the levels aren't actually consistent with the observed flood marks around that gauge, but the timing is thought to be correct. So we've included it in there, but made a note that the actual water levels are likely to be too low in the recorded data. So that's our starting point for the model, is our calibrated 1D, 2D model. So what happens if we replace that 1D in-bank with 2D? So in this case, I'm leaving the culverts and pipes and bridges as 1D structures within that 2D, and linking those dynamically. So in TUFLOW terminology, that would be an SX connection, which is a flow boundary to the 2D cells and a water level boundary to the 1D, so a dynamic connection between those. We've also switched from a fixed 10-metre cell size across to a Quadtree solver, where we're actually setting the level of refinement. And the reason that we've done that is we're trying to get some decent resolution in the channel. So this map over here shows in the light blue, that's all the road layers. We've actually got a level 3 refinement. So that's down to about 8 metres, and level 4, which is the main dark blue, is the main channel. So we're down to about 4 metre cell sizes in there. But as the channel gets bigger, we've gone to level 3 down there and level 2 at the outlet. So we did quite a lot of, before we kicked off all of this research, we did some cell size sensitivity, and we found that this gave us a pretty good representation of what was going on, also with reasonable runtimes. So it took about 1.5 hours for that to simulate a 25-hour storm event on a half-decent GPU. So as we zoom in, that's what the output grid looks like, or the mesh looks like. And if we zoom into even further to a channel, that's the type of resolution that we've got in some of these urban channels. And there's some examples of depth and velocity outputs from that 1D, 2D, sorry, the 2D model. There's the 1D, 2D calibration. And if we pop on our 2D, which I showed the depth and velocity outputs for before, the maps look quite nice, but maybe they're not as accurate as the 1D, 2D result in this case. So notably, we've made no changes in the inputs, like the Manning values and things like that have all stayed the same between the 1D and the 2D model. But in this case, we are certainly getting a higher water level typically, and it's also a little bit lagged. If we compare a histogram of those calibration points, it might not look as, the calibration is certainly not as good over here. So in the 1D, 2D model, so the 1D in-bank, this is where we ended up with a root mean squared error of about 0.18. With a 2D in-bank, it's gone up to about 0.22, and there is a bigger spread, but it might not be as bad as it looked in the gauge, but it's certainly not as good. Why is that? Why is it not as good with the 2D in-bank? When we're comparing the 1D and the 2D, there's some things that are handled differently, with the 2D probably representing more of those losses, like junction losses and turbulence losses and things like that, as we've seen, which weren't accounted for in the Manning's, in the 1D model. So an example of that would be a junction. So in this case, if we've got a flow junction, we've got a main channel flowing in here, we've got a tributary flowing in, and then we're seeing quite complex hydraulics at that confluence. And the losses that occur there vary obviously with the angle of that inflow, which is going to stay the same throughout that simulation. But they're also going to vary based on the flow and the momentum ratios of the relative channels. So the 1D doesn't really capture that, and so there'd typically be a form or a bend loss needed to be added by the user to account for some of those losses. So that's an example there of that photo's taken where we've got flow coming in at an angle, sort of almost at a right angle to that main channel. So that was actually taken in this catchment on the 1990 flood event, the event that we're looking at. This photo was probably captured about 3 hours after the peak, but we can certainly see that there's some pretty wild turbulence happening there in that main channel. So if we have a look at, so that's an overhead view of one of these confluences. And if we add in some 2D results, What we're now starting to see is over here, we've got an increased area of high velocity as the effective flow width across there decreases. And that generates additional turbulence, and the 2D captures some of those loss effects where the 1D doesn't. It's most likely that the calibrated, so the 1D 2D model was calibrated, so the values that are used in that calibration might be slightly high to account for some of the effects that are not captured in the 1D, such as the turbulence and the junctions. So what we did was say, well, maybe we'll reduce the Manning's value, keep them within industry standard ranges. So notably for the in-bank concrete line section, it was calibrated to about 0.018, which is probably at the higher end. So if I run that again with a lower value of say 0.013, there's the difference between those results. So we can see there that the thinner line is the original 2D in-bank, with a thicker line now being with the lower Manning's value. So it's helped, but it's not really been the magic bullet to fix the difference between them. The other thing that is quite prevalent in this model is there's quite a number of structures across that open channel, and a lot of those are actually either clear spanning or with marginal abutments. And what's happening there in terms of losses actually becomes quite important to the system. When we're modelling those as 1D in TUFLOW with 1D upstream and downstream, those losses actually get adjusted based on the entrance and exit velocities. So if there's no change in velocity, so in this case here, we've got a bridge, which actually isn't from this catchment, but it's a pretty good example, which is where the flow area under that bridge is very similar to the flow area in the channel. We wouldn't really expect to see a change in velocity right up until we start to get into these abutments. So if we apply those losses unadjusted, those losses will be applying even at lower elevations. So what happens in the 1D is they're adjusted based on those equations there. Moving to 1D, 2D, we either need to lower those loss values or allow TUFLOW to dynamically adjust those based on the 2D approach and departure velocities, which has been built into TUFLOW, but is not the default for those SX connections. So over here on the right, we've got the same model with fixed losses. In this case, the darker losses, the darker line there is a case there with those losses being adjusted in there. And we can see it is starting to bring it down, particularly that lower gauge. But once again, it's still not entirely the whole answer. And there's certainly very good evidence of high velocities around those structures observed in this model. So as part of this study, we provided some design mapping to council, and about a week later, there was a significant storm event in 2007. For those of you who remember it, the Pashabolka ship washed up on the Nobby's Beach in Newcastle, and there was also a significant flood event as well. So Bill and I actually went down there after that event and wandered around and compared our flood maps to what was observed on the ground. And we can certainly see that, in this case, fences upstream and downstream have absolutely been flattened. Not sure if you can see it, but not only has it been flattened, it's actually sheared the metal off. There's Bill walking around with here 1 in 100-year flood maps, actually comparing to what happened on the ground. This is at the downstream of a crossing, and we can see huge velocities, lots of scour, and we can actually see that the direction is now inwards. It's washing things back into the channel. Velocity is so high that some of these big concrete sections have actually lifted and shifted. This one's at an upstream of you can just see the head wall in through there. And what we're seeing is water jumping out of that open channel, actually going over the land, across the fences, across the road, and then back into the section downstream. And this is actually the same crossing. You can see the fence flattened out there. The force of the water there, the velocity of the water there is high enough that it's actually lifted up and picked those concrete slabs up and just thrown them around. So certainly very strong evidence of high velocities there. And that's why we do need to include those loss adjustments in there. And this is on the downstream, we actually can start to see the fences are actually flattened in the opposite direction as water's making its way back into the channel. And here we've got another case there where we've got water coming back into the channel and actually scouring out underneath concrete slabs and houses. So there's certainly strong evidence to support the loss adjustment, but it's still not quite been enough to get it there. Obviously, with that compound channel, we found that switching to an anisotropic turbulence helped out a lot. So doing the same thing here. So in this case, we've got the isotropic turbulence case, which I just presented previously. And if we jump that to the anisotropic with a transverse of 0.5 and a longitudinal of 7, we're starting to see that those levels are coming down much closer to with what was observed. So comparing that back to the 1D in-bank, what we've done is we've lowered the Manning's value in the channel. We've adjusted those the structure loss based on the 2D velocities, and we've also switched from an isotropic turbulence to an anisotropic turbulence with different values. So in this case, the orange line, or the darker, thicker lines, are the original 1D in-bank, and we've moved across to the lighter, the thinner lines, which is the 2D in-bank. So we're getting a reasonable time series, and if we actually compare that histogram of those calibration points, of those 27 grade 1 calibration points, we actually can see we're very similar. Our root mean squared error is very similar. We've actually got more of those points in the highest plus or minus 0.05 band, but our mean and median are quite similar, and we're getting a similar level of calibration. So that's quite reassuring. So pros and cons of using 2D instead of 1D for open channel. The pros would be it's faster to set up, and then it's more computationally accurate. It's capturing more of that velocity variation across the channel, or it's capturing velocity variation across the channel, and the turbulence losses associated with that, as well as the junctions where we've got some quite complex hydraulics that the 2D is able to capture, which the 1D isn't. And that also gives us better velocity computations and interactions with those over blank areas. And so keeping this solution fully in 2D provides a better transfer of momentum from the main channel into the over blank areas. And it's also much easier to produce our mapping, so we don't have any 1D, 2D interfacing to deal with in terms of model setup and also mapping as well. The cons, long runtimes are longer, so that's less of an issue with GPU acceleration, but we will see a longer runtime with 2D in-bank, particularly as with a dynamic time stepping that's being used. If we do have high resolution cells in areas where we've got deep water or fast velocities, they're much more likely to be limiting the time step. So in this case, the model was being limited by the smaller cells in that main channel, which is where we needed to resolve those hydraulics. So it's run times were certainly not unyielding at all in this model. An hour and a half to run that large model for 25 hours of simulation time. But it's probably something that we probably need to see more calibration cases before it becomes too mainstream. Okay. Other outcomes coming from that, we certainly see the benefit of subgrid sampling, as well as the Quadtree or flexible mesh to create those smaller cells in-bank. And dynamic adjustment of those structure losses, those 1D structure losses, even when coupled with 2D models to account for those approach and departure velocities, which is a similar approach to what's done with 1D. And the 2D in-bank Manning's, I think is consistent with some previous webinars that we've done, might have to be a little bit lower than 1D, or probably more more correctly, the 1D Manning's values that have been used, and in this case were calibrated, were probably a little bit higher to reflect some of the physics that weren't being captured in that 1D engine. Such as the turbulence and the shear between those in-bank and over-bank areas. And certainly the anisotropic turbulence is showing some improved calculations of those velocity distributions across those channels. So watch this space on that one. We'll keep developing and testing that, and with the aim that that will be in the 2021 version of TUFLOW. And finally, we'll jump across to some questions. Give us a little bit of time. So that's a photo we took down there at Nobby's Beach of the Pasha Bulker washed ashore. Didn't anchor far enough offshore, and that big storm event washed on shore. It was quite the sight. It looked really out of place sitting there washed up on shore.
Brilliant presentation, Phil, and that is that photo. I remember it clearly. What a big event that was. Yeah, I know. Look, you've covered a vast amount of material there, and it's just awesome.
Sorry, but I had some building works that I was unaware were going to happen. I'm not sure if much of that background noise got picked up, but it seems like they started jumping up and down on the roof above me, which is really unfortunate timing.
No, that's all right. Press on regardless, and your voice was louder than the tapping, but that's great. Okay, now, to handle this Q&A, Bill, will you come on screen and facilitate questions coming on board? So if you and Shuang could proceed from here, I'll just stand by.
Thanks, Trevor, and great work, Phil, given the banging above your head.
Very distracting.
Trevor was asking me whether I should jump in, but then he said that you seem to be coping. So
if I wasn't on there, I would have gone out there and said, could you please keep it quiet? But it's a bit hard to do that when you're in the middle of a webinar.
It is. Yeah, it certainly is. Can you see the questions there, Phil? There's a couple there. The one there by Wesley Pereira. A rural catchment today can become an urban catchment after some years. Is it appropriate to treat the catchment as urban for modelling? Well, basically the approach should be that you should, if it's going to become urbanised, then you should be looking at that as a scenario within your modelling, because urban catchments will push the water off a lot more quickly than rural catchments. You can see quite significant changes sometimes, particularly particularly if a large percentage of the catchment becomes urbanised. So the answer is yes, but that has to be built into your various scenario modelling, which is normally driven by council regulations or government regulations.
Yeah, usually there's certainly approval processes that have to go through before an urban area becomes, a rural area becomes urban. I know certainly here in New South Wales that there'd need to be quite a detailed flood impact assessment done for those sites where you're able to show that by going from a rural area to an urban area, the change in land use and potentially channelization associated with that is not going to make it worse for your neighbours. If by doing that you're making flooding a lot worse for your downstream neighbours, certainly here in New South Wales that wouldn't be approved.
So Christie's asked, what would your recommendation be for modelling culverts and not bridges?
And I think that the traditional or the typical approach of having those as 1D elements embedded is probably the right thing to do. Just having those linked through to the 2D. Bill, I'm sure you've got an opinion on this, but the 1D, having those as 1D culverts will allow those to switch between inlet and outlet control flow regimes, and there's a whole range of things that it will test for in TUFLOW and dynamically switch sort of to the right flow regimes and things like that. But with the 2020 10 version of TUFLOW that went out, there's the option in there for the SX adjustment, which will allow the entrance and exit losses to be adjusted based on the velocity in the 2D. So if it's a large culvert underneath a road embankment or something like that, where the velocities upstream and downstream are likely to be relatively negligible, then that probably isn't so important. But if it is, culverts in a main channel and you're linking that to 2D, you'd certainly need to be looking at by reducing those losses to make sure you're not, applying losses that are too high. If you're applying lots of entrance and exit losses, whereas in reality the water's basically shooting through a channel, shooting through a culvert that's the same size and back out the other side, you might see too much head drop across there.
Yeah, if you don't adjust the losses, yeah.
Yeah, if you don't adjust the losses, yep.
Yeah. Okay, so Craig's asking, the US is an interesting region in the sense that they're big investment in 1D models for FEMA mapping requirements, and they would all be predominantly HEC-RAS models. Any thoughts on using full 2D flow models for FEMA delineations? The UK Environment Agency has stated a preference for 1D, 2D, under the impression that 1D, 2D will be more accurate. Well, just on the UK, yeah, I mean, that situation in the UK is very much on good reason, and that is partly because, well, once again, they have a big investment in existing 1D models, and a lot of those models now have 2D floodplains, typically TUFLOW, and they and one of the big issues in the UK is somewhat different to Australia, is that it's just very hard to get the bathymetric survey for the rivers. They have water in them all the time, whereas Australia tends to dry out, and we tend to find our creeks and rivers, the narrower, higher ones, easier to survey. But as Phil talked about, and also Duncan, our guy in the UK, Duncan Kitts, he's just given a presentation at Floods and Coast Conference there, that it's really, the time is now right to seriously consider using 2D in bank, but that's only because of the reasons that Phil outlined in the presentation today. And the big ones are that the data collection is now much more cheaper or feasible. You need to have something like subgrid sampling. You still need to get a small cell size sometimes just to get your nice velocity distributions inside the riverbank. And that's where Quadtree helps a lot. And so, and the other big plus, of course, is GPU cards, and the much faster simulations that we're now achieving is making us be able to do all that. So the UK EA, I suspect, will, I mean, the industry will shift, and these models lie around for quite a long time, so you don't change them overnight. So, both the UK will shift more to these types of models. They don't do the 1D cut through the 2D. There are a lot of benefits not having to do it in 1D. And I suspect the US will tend to follow suit a bit more, but there's a lot more regulation in the US, so that tends to constrain things at times. So, but you will need to have all those features and functionality and so forth.
Yeah, but there's other benefits I don't think I mentioned in there, but things like calculation of super elevation. Most of the 1D schemes don't have a super elevation calculation, and if they do, it's sort of based on empirical, whereas, where you've got particularly high velocity channels and channels that are sinuous, that can become important as well as some of the other things that we did talk about. So I certainly do agree with Bill that probably there will be a more change going that way.
So Rudy's asking, aren't losses calculated by the change in velocity? So the loss coefficient has little influence as velocity differences. Not great. No, well, losses from a bluff object such as a pier or a bridge deck, or whatever, is related to the v squared on 2g. So it's not the change in velocity, it's actually the v squared on 2g. It's a dynamic head. You're losing that kinetic energy that's in the water when you hit a bluff object. So that's where we have these loss coefficients on top of that. Now that loss coefficient, if you don't have a change in velocity, then you don't have a loss. So you have to adjust these loss coefficients down or up depending on the approach departure velocities. That's sort of been, you can derive the second equation, the exit loss, from theory, which is just a momentum balance across the outlet of a structure. And the entrance one is a bit more complicated because the losses are actually occurring due to water expanding inside the structure after the venocontractor. So the entrance loss is actually really an expansion loss, but inside the structure. So so there is that formula which has been derived through flume tests. So yeah, so the losses around structures are all related to the v squared on 2g. And the loss coefficients do need to be adjusted depending on the approach and departure velocities. Richard Sharp is asking, will the anisotropic turbulence coefficients be cell size dependent? No, because it's an extension of the Wood turbulence model that we built into HPC 2020, and Greg and Shuang have been doing a fair bit of research and actually tied it back to some literature and it's actually very commonly known also in the advection dispersion world that the longitudinal dispersion, if you like, is much stronger than your transverse. So there's an increasing amount of evidence, and we're just getting much nicer results for velocity distributions across something like that trapezoidal channel that Phil was showing. But yeah, it's also an extension of the Wood turbulence model, which is cell size dependent, or cell size independent, I should say. Is HEC2 no longer used for modeling? That's not sure. I can't answer that one. HEC-RAS is used a lot. HEC2, I think, was the forerunner of HEC-RAS. Yeah, can't answer that one. Sorry, Wesley. So Rudy is also asking, other models have been using 2D in-bank since inception. Yeah, absolutely. And we've got lots of more major river models where 2D is used in bank. It's just that when you have a situation like Throsby Creek where you've got a tiny channel, you just can't get your 2D resolution down fine enough. So look, we've been wanting to do 2D in bank for these types of models for years and years and years, but you just can't get your 2D cell size down small enough.
Yeah, and something like the Brisbane River model, which was 2D in bank and really well calibrated. I know we've done webinars on that. So yeah, absolutely 2D. It's just where you shift from doing fully 2D to 2D 1D. It seems to be coming down, and that partially probably because there's a strong preference to have it in 2D because it's easier to set up and it's probably more correct. 70-something% would prefer to see it in 2D.
Yeah. So I think with these new features, we can increasingly move to using fully 2D, except for structures, except for culverts. They'll always be done in 1D pretty much, except for the larger bridges and larger culverts we do in 2D, if your cell size is small enough. But you won't get rid of 1D. Pipe networks, etc., will always be 1D.
And you have an upcoming webinar. Is it October, Bill, on modelling of structures?
So our October webinar, we will be exploring all the challenges to modelling structures, and particularly in 2D. I mean, 1D is well established. There are issues, as Phil raised today, about how you deal with your approach and departure velocities when you've got a 2D, 1D, 2D link. We're really doing some looking into the challenges of modeling structures in 2D, and we've got some nice stuff already to show for that.
Christie's. I think that's a response to Christie's.
How about the bridges?
Yeah, and I guess the bridges, they can also be modelled in 2D and hang around for the webinar later in the year on more information about that, I guess, is the answer to that one.
Yeah, well, we certainly are addressing bridges big time in the October webinar. Yeah. I think we might have done the questions for once.
That's fantastic. We got through them. I know.
And we're bang on time.
Totally amazing. We're bang on time. Guys, it's been a fantastic effort. Thanks so much, Phil, Bill and Shuang. It's been really good. We've got through a lot of material and people have stayed with us. I just want to remind everybody that there will be a survey pop up just after the webinar ends. So be ready for that. We'd love to have your responses. And we will be sending a recording out to all the registrants for this webinar. So fantastic to have everybody here today. Please join us again for the next free webinar. We look forward to your company. TUFLOW webinars coming up in the 15th September, 20th October, 17th November, and also thirdly, the live courses. They are going gangbusters. So do join us. There's lots happening. Once again, we really appreciate your being with us today, everyone attending. For Phil, Bill and Shuang especially, and a big shout out for the Australian Water School staff, Joel Vortman and Joe Olmeyer. Thanks so much for everything you've done. A lot of support for these sort of webinars, and it comes with a great deal of enthusiasm. Once again, thank you very much, everybody. See you later for now. Bye, Phil. Bye, Bill.
Thanks, Trevor. That was excellent. Yeah.
Thanks, Trevor. Thanks, everyone, for joining.
Yeah.
Bye for now.
Thanks for watching. Subscribe by clicking the link below and click on the notification bell to stay up to date with new releases. For the latest in significant, innovative and critical advances in water science, technology and management, subscribe now. To build your skills, enhance your technical knowledge and learn from leading experts in water, visit theaustralianwaterschool.com.au and discover our online training courses, both live and on demand.